Hi everyone, today I want to introduce SGBA, a new way to improve LiDAR-based mapping using semantic understanding. Mapping in a dynamic scenes is messy. Think about environments with moving objects, featureless roads, or sensor noise. Standard LiDAR odometry just isn't built to handle that. Disturbances throw off pose estimates, and errors slowly creep in. And here's the key problem. Local disturbances don't stay local. They get amplified as the robot moves, causing the entire pose and map to drift significantly. Most existing LiDAR bundle adjustment methods depend on point or plane features, flat walls, road surfaces, or other rigid geometry. But what happens in a park? Or a construction site? Or a curved hill with no strong planes? Those methods break because they rely too heavily on geometry that isn't always there. We address this by proposing SGBA to changes the game. Instead of relying on specific geometric shapes, we model the entire environment as a semantic Gaussian mixture model. It captures both where things are and what they are: roads, cars, poles, trees. This richer representation lets us adapt to the scene rather than forcing the scene to fit our model. The system works like this. First, we segment the point cloud by semantic class. Then we fit Gaussians to each class and check whether the optimization is well conditioned. If not, we add more semantic layers until the system is stable. This means we're only using what we need to solve the problem. No more, no less. And instead of forcing each point to match a specific landmark, we utilize a soft, probabilistic associations. This allows SGBA to gracefully handle noise and uncertainty, especially when the initial pose estimate is poor. It's like giving the optimizer room to breathe instead of boxing it into a wrong assumption. As shown here, SGBA significantly reduces odometry error and outperforms existing methods like BOM, especially in scenes where planar features are insufficient. By using semantics and probabilities, we maintain accuracy even in the presence of sparse features and disturbances. Here's a great example. A completely flat scene with almost no usable planes in the other direction. Plane-based methods just fail. But SGBA leverages semantic cues like lane markings and grass edges to still perform accurate refinement. Semantics save the day. Across multiple datasets, Kitty, OS 128, Livox, SGBA consistently delivers lower error. Even in noisy or degenerate scenes, it avoids divergence. And the adaptive semantic strategy keeps it efficient, competitive with BOM in runtime, but far more robust. So to wrap up, SGBA brings three core contributions: a semantic GMM for general landmark representation, an adaptive layer selection to avoid overfitting or underconstraining the problem, and a probabilistic data association that makes it resilient to noise. We believe this brings LiDAR mapping a big step closer to true real-world robustness and potentially for robust embodied AI interaction by giving AI agent better spatial and semantic understanding. Thanks for watching. For more details, please refer to our paper.